Selective precipitation. What is the range of silver ions that you can add to precipitate the first precipitate, whatever it be? So another way that you can ask us is this could be a silver nitrate and there can be a metal in front. So the first step is to find out who will precipitate first. So if you do have a metal in front, to dissociate them all, mix and match, and find out who can form a solid in this new solution using solubility rules. Now we would compare who is more soluble and less soluble. That usually depends on K, and the smaller the K, the less soluble it is. But because this is a 1-to-1 ratio and this is a 2-to-1 ratio, we cannot just compare the KSPs because their KSP is dependent on x2 for the first one, while the second one is dependent on 2x squared times x. So I made another video on this section, but for the sake of being condensed here. So that tells us that essentially with a KSP coming from the data table, the x for this first one is going to be, where do I have it here? 8, so this is 1.34 times 10 to the negative 5, and the second one is going to be a larger x, which is molar solubility, which means the second one here has more aqueous ions, so it's more soluble. So the first one is less soluble, so this will be the first precipitate. Now, having found who will precipitate first, next we have to answer the question, what is the range of silver ions needed to precipitate the minimal amount of silver chloride and the maximum amount of silver chloride? So the process is very mechanical and simple, provided that you don't make weird errors like forgetting their their powers. So that's why I would advise for this step, just write out their ice table so you remember that Ag here is going to be to the power of 2 because of the coefficient. Yes, please. And chromate is to the power of 1. Now in both of these steps, we're going to be isolating for that aqueous solution which we're adding, which is in both of these cases silver. We're isolating for silver, and these other concentrations will just be the existing concentration already in the solution, 0.1 molar. So here it's going to be KSP 1.8 times 10 to the negative 10 divided by initial amount present, and that will give us a concentration of Ag plus, which is going to be 1.8 times 10 to the negative 9 moles per liter, while here we have to isolate for this which we're adding. So the KSP is 2.5 times 10 to the negative 12 divided by the initial concentration already in the solution. Make sure to square it because of the way we set it up. Okay, don't forget about that. So that will give us a concentration of 5 times 10 to the negative 6 molar. So this is the minimal amount of silver ions that you can add to precipitate the first drop of solid of silver chloride, while this is the maximum amount of silver ions you can add to precipitate the last bit of possible silver chloride. And going beyond this concentration will get you a second precipitate. So there will be 2 precipitates instead of 1 when you go beyond this concentration. So this is a range of silver ions needed to precipitate. Now sometimes they might also ask you to prove it or to calculate the percentage that has been precipitated. So the same process, just write out the KSP for that thing which you want to precipitate. And this time you want to check how much is precipitated when you add the maximum amount of silver ions possible. So now we're going to isolate for chloride because we want to test how much chloride remains when we add that amount of maximum silver ions. And these are all to the power of 1. Good. Chloride, that will give us 3.6 times 10 to the negative 4 moles per liter. And the last step of checking is to verify how much of it has been dissolved. So this is the final amount remaining divided by the initial concentration times 100, and that tells us how much remains, which is very small, telling us that this was an effective precipitation when we add this amount of silver ions that will precipitate practically everything relating to chloride.